In this lesson, we want to define what it means to have a rational exponent, something like an exponent of 1/2 or 1/3. So before we actually evaluate these two expressions, which you can do on a calculator, I want to look at something that we're familiar with. So to start with, like 5 squared, for example, I know is, well, it's 5 times 5, and therefore the answer is 25. Or if you had something like -2 cubed, well, again, that's -2 times -2 times -2. This time I'll just write -8 as my answer. It's going to be negative because there are 3 negatives. The idea of an exponent that's a fraction reverses these two things. Like, how can I get 25 to go back to 5? Or how can I get -8 to go back to -2? So next to these two examples, that's what we mean by a fraction exponent. So when we have 25 to the 1/2, it's what number that when you square it gives you 25, and therefore the answer is 5. So written another way, this is just the square root of 25. And sometimes a 2 is written here to indicate that it's the square root, indicating that we're dealing with a fraction of 1/2. Likewise, for -8 to the 1/3, it's going backwards from cubing. So you're thinking of what's the number that when I cube it gives me -8? Well, I know the answer now is -2. So written another way, we'd say the cube root of -8 is -2. So that's what these fractional exponents mean. They mean either like a square root or a cube root, a fourth root, a fifth root, and so on. They're going backwards from powers that we are already familiar with. So maybe just to try a couple of others, let's see. How about 125 to the 1/3 power? Again, this is something that you could type right into a calculator and it's going to tell you the answer. But if you don't know what it is, like you're trying to figure it out, well, the answer would be, well, what number when I cube it would give me 125? Again, going backwards from cubing. So you just try a few numbers, and I'm punching this into my calculator here, and I see that it's 5. The answer is 5. This says that if we take the cube root of 125, it is 5, because if you cube 5, it would give you 125. And likewise, if you had -125 to the 1/3, this is the cube root of -125. So the answer is just going to be -5 this time. So maybe just to check a couple of others, maybe another good example would be 256 to the 1/4 power, or the fourth root of 256. Again, when the numbers get larger, it's kind of hard to figure out what the exact value is, but this is going to be 4. The reason being, if you take 4 and you raise it to the 4th power, it would give you 256. The only other thing that could possibly be an issue here is, well, what if you did -256 to the 1/4 power? What is the answer here? And anytime that you're dealing with this even number in your exponent, like a 1/4 or a 1/2, and you have a negative number that you're dealing with here, there's an error that you will get. And all this means is there's no real possible answer to this expression. Because, well, whatever the answer is, if you raise it to the 4th power, it has to be positive. So whenever you have a 1/4 or 1/2 or 1/8, you can never apply that to a negative value because it would always give you an error. And your calculator would tell you this too. So again, for this example, it's just to understand what it means to have a fraction in your exponent instead of just a standard integer. And basically it just means go backwards from something that you are familiar with. And so continuing with this idea in example 2, you don't just have to have fractions like a half or a third, but you could have something like 2/3 or 3/4 that appear here. And if you understand the previous example, this isn't much more difficult. So let's start with -8 to the 2/3. So what this will mean, it's going to be a 2-step process. So you're going to still take the cube root. Like when I see 2/3, like I first am kind of like thinking, oh, I have a 1/3, and then after that there's then this 2 that's being multiplied after it. So you still have this cube root, but now it's going to be of -8 squared. So if your fraction is something like 2/3, this is often referred to as your power over your root, because you're still cube rooting, but you first are going to square the value before you apply the cube root. So let's try this out. So I'm taking the cube root of -8 squared. Well, if you were to square -8, you get 64. And so now what is the cube root of 64? And you could just try to think of some numbers to see what works. There's a lot of ways to break this apart. I know that the answer is 4. You can just kind of think of some numbers, and 4 times 4 times 4 is 64. I'm just going to check that out, and it is. Another way you could break this down is to, well, this is the cube root of 64 is 8 times 8. And if we're dealing with a product here, you could actually take the cube root of both of those values separately. And I know the cube root of 8 is 2, and well, the cube root of 8 is 2, and the whole answer would be 4. So it's kind of like how you'd like to go through this process. For me, when I got to here, I just was trying to think of a number that would work nicely, and 4 happened to be a small number that worked out really well. In general, it could be impossible to guess the answer, but for anything I give you, like, it should be something that you could figure out relatively easily. And so as the last example, we have 81 to the 3/4. And so this one is now dealing with the 4th root of 81 to the 3rd power. So if you were to just directly, follow order of operations in your calculator, like, this would get pretty messy. It's the 4th root, and if you take 81 and you were to cube it, you get 5, 3, 1, 4, 4, 1. And then you would take the 4th root of this number, and it tells you 27. So like, that's like not a good way to approach this if you're trying to like do this in your head. Like, I did that all on a calculator. But you could try to break it apart a little bit differently. So what I'm going to do is actually reverse the power versus the root. I'm going to do the root first, and then I think the power second. Because 81 is positive, I'm not going to run into any problems of taking an even root of a number and getting an error message. So I'm really going to look at 81 to the 3/4 as, well, first I'm going to take the 4th root of 81, and then whatever answer I get there, I'm going to cube it. Now let's see, the 4th root of 81, it's going to give me a smaller number, which is already nice. So I have to think of something that when I raise it to the 4th power would give me 81, and that's not too bad. That's going to be 3. And what happened here is we have, well, 3 to the 4th power. That's 3 times 3 times 3 times 3. 3 times 3 is 9, and 9 times 9 is 81. Great. And then we have 3 cubed, which is 27, and what do you know, our answers match up. So for this example here, same idea as example 1, but now we're just throwing in a power, 2 and 3, but it could really be any fraction. So for example 3, the difference here is going to be we're taking square roots and cube roots, and the numbers aren't going to work out to give you nice values. So like if you're doing this right on your calculator, I'll write it off to the side, but we have the square root of 20. So I'm going to type that in, see what it tells me, and yeah, I get a decimal. I get 4.47, and it goes on forever. This is going to happen for most numbers that you take the square root or cube root and so on of. But in terms of the square root of 20, you can still break this down into something that's simpler to think about. Here's what I mean. If you're trying to compute the square root of 20, think about just the number 20 itself. If you can break 20 apart into something that you can take the square root of nicely, that's going to give you a smaller number to work with. So by that I mean 20 is 4 times 5, for example. And 4, if I take the square root of 4, it gives me 2. So I'm breaking 20 apart into 2 numbers, one of which at least the square root will be nicely for. So if I work this out, the square root of 20 is the same thing as saying the square root of 5 times 4. And, well, that's the square root of 4 times times the square root of 5. I can break that apart if I'm dealing with a product. And the square root of 4 is 2. The square root of 5, it's going to be a mess. It's going to be a decimal, but I've now changed it to a more simplified number. So this is my final answer. So I didn't get it down to one integer, but I did take it from something a little bit more confusing to something that's a little bit easier to think about. So that's one way you can simplify values that have square roots or cube roots. If it doesn't work out to give you a nice integer, try breaking it down a little bit. So let's try it for the remaining ones here. So let's say, the square root of 28. Let's see. Well, you take your first attempt here, and 28 is 2 times 14, but neither of those numbers, if I take the square root of it, is going to give me something nice. So, okay, that didn't work. So, I try again. So let's see, 28. That is 4. Okay, this one now is 4 times 7. Okay, I'm getting that 4 again. I think that's going to work nicely here. So the square root of 28 is the square root of 4 times 7, which I can break apart into the square root of 4 times the square root of 7. Square root of 4 is 2. I can't break apart the square root of 7 any further, and here's my final answer. I've simplified the square root of 28 down to something a little bit simpler. So this same idea should work for cube roots or fourth roots and so on. So let's try it for, let's say, the cube root of negative 81. The nice thing here is I know the answer is going to be negative, so I could really just think of this as negative the cube root of positive 81, just so I can ignore that negative that appears in here. Okay, the cube root of 81. If I try that in my calculator, again, it's not going to give me a nice number, but what I'd like to do is break 81 into something that has not a nice perfect square, but something that has a perfect cube. So let's see, 81, I know it's 9 times 9, but the cube root of 9, okay, that's no good, so I'm just going to erase that. Another option would be 3 and 27. This is going to work out really well, and the reason is the cube root of 27 is perfect. It's 3. Let's apply that in this problem. So picking back up, the cube root of 81 is the same thing as the cube root of 27 times 3. So this is negative the cube root of 27 times the cube root of 3. The cube root of 27 is perfect in that it's 3. The cube root of 3, I can't really do anything with that. It's kind of a strange looking answer, but here it is. Negative 3 times the cube root of 3 is the same thing as the cube root of negative 81. And so lastly here, let's work on the cube root of positive 16. All right. So 16 is 4 times 4. That's not good. What about 2 and 8? Okay, this is going to work out well because the cube root of 8 is 2. So let's write this out. This is the cube root of 8 times 2, which I can break apart into the cube root of 8 times the cube root of 2. The cube root of 8 is 2, and what is left over is the cube root of 2. So I'm basically just trying to break apart the number into things that I know are perfect cubes. And you can verify all this on your calculator, but these are just simplifying numbers instead of just simply writing down some type of decimal. And for the final example, so now we're going to start throwing in some variables to see how this switches things up a little bit. So what I'd like to do is use the ideas from example 3 to simplify expressions that have maybe x's or y's or so on in them. So I'll start with the square root of 16x to the 4th y squared. So this is going to actually be quite simple to simplify. And here we're assuming that all of our variables x and y are going to be positive numbers or 0, just so we don't have to worry about if we take the square root of a negative number or something that it is going to give us an error message. So anyway, for the square root of 16 times x to the 4th times y squared, like in the last example, I can break this up into the following. I'll just break it apart into each piece. 16 x to the fourth and y squared. So the square root of 16, that's easy, it's 4. And now I'm left with these other two pieces. If you go back to thinking of, we have x to the fourth, and the square root is really a 1/2 exponent. If we apply our rules of exponents and multiply these two values together, we get 4 times 1/2, which is 2. This means that the square root of x to the fourth is x squared. If we do that same thing for the square root of y squared, so this is y squared to the 1/2, and if I multiply these two exponents, 2 times 1/2, you actually just get 1. And this means that we have y to the first power, which you don't have to write that one, but this makes sense. If you take the square root of 4, you're cutting 4 in half and dropping it down to 2. If you have the square root of y squared, that 1/2 exponent is dividing this 2 by 2, giving us 1. So again, assuming x and y are positive, we have our answer of 4x squared times y. So let's try that again for maybe something slightly different where it won't work out so perfectly, like 32 x to the fifth y cubed. So it's like now we have a problem. If you take half of 5, you're going to get like maybe a decimal, or half of 3. It's not as nice. But I can still break this apart. But before I do that, I'm going to break things apart, so I'm going to write each piece so it has an exponent that will divide nicely by 2. So for 32, let's see, that is 16 times 2. The 2 is left over, but the 16, if I take the square of it, it would give me 4, so that's good. Now with x to the fifth, I'm going to write that as x to the fourth times x to the first. The reason is the square root of x to the fourth drops down perfectly to just x squared. Now for y cubed, that's y squared times y. I've now written this in pieces where the square root will work nicely with 3 of the terms, those being here, here, and here, and the remaining stuff I'm just going to leave under the square root. So let's write this out. So if I start with the square root of 16, I get 4. I then have the square root of 2. Okay, the square root of x to the fourth is going to be x squared. The square root of x to the first I can't do anything with. The square root of y squared is just y. And then the square root of y I have to leave as is. Like, this would actually be a somewhat acceptable answer. You took the square root of each piece, and everything that didn't work out nicely, we just left it over. You could write this a little differently. Maybe put the 4, the x squared, and the y next to each other. And you could even, under just one square root, leave the 2, the x, and the y. You could just like group it back into one piece. So here is one way to express your final answer. We took the square root of things that were nice, but in this example, there just happened to be some stuff left over where the square root didn't work out very nicely. And so for the last piece, we have the cube root this time of 125, x to the 9th, and y to the 7th. And the thing to note here is, if you're dealing with a cube root and you have a 9, that's going to work out great, because if we take 1/3 of 9 we get 3, it's perfect. But here if we have 7, well, 3 divided into 7 isn't nice, but you could break 7 into 6 and 1. The 3 divides nicely into the 6, but it just leaves us with the 1 left over. So let's start writing this out, where I'm going to take the cube root of 125. From before, I know that's nice, it's just 5. So let's start writing this in pieces. So I have the cube root of 125. I don't have to do a thing with that, nor do I have to do anything with x to the 9th. But y to the 7th, I'm going to write as y to the 6th times y to the 1st. And now I'm going to take the cube root of each piece. The cube root of 125 is 5. The cube root of x to the 9th is x cubed, because I'm just dividing 9 by 3. The cube root of y to the 6th is y squared. And the only thing left over is the cube root of y to the 1st. And this is my final answer.